Hey everybody, today I'm going to prove the linearity of summation. Basically, the sum of AF plus BG equals A times the sum of F plus B times the sum of G. Where F and G, they're functions, they could be just anything, any sequences, whatever is just dependent on the index, which in this case is I, and then A and B are just constants that aren't dependent on I. So, this shouldn't be a very difficult proof, it's just based on induction. So let's start off with the base case. So base case, basically we're going to start with, it doesn't have to be I equals 1, we could start with I equals 0, but I just usually start with 1. So the base case is going to be n equals 1, right? This makes the most sense here. Okay, so with the base case, all we're doing is we're taking the sum from I equals 1 to 1 of AFI plus BGI. And if we have the sum from 1 to 1, all that is just this itself, but evaluated at 1. So all this is just going to be AF1 plus BG1. And that's it. And now this is pretty trivial because all we can say is this is going to be A times the sum I equals 1 to 1 of F sub I plus B, and then same thing for G, I equals 1 to 1 of G sub I. And that's it, because this is just equal to F sub 1, and this is just equal to G sub 1, and so we're done. So this is the base case proven. So now the induction step. So the part I omitted is the induction hypothesis. All that says is, let's assume that this statement is true for n equals k. The induction step is saying, okay, assuming that's true, what about n equals k plus 1? Okay, so let's do that. So the sum here from I equals 1 to k plus 1 of A sub F, AFI plus BGI. So what's this going to be? Well, we can split this up into the sum from 1 to k and then plus just 1, right? Evaluated at k plus 1. So the way we can think of this is the sum from I equals 1 to k of AFI plus BGI. And then plus, so it's going to be this, plus AF k plus 1, k plus 1, and then plus BG k plus 1. Right, so if we take these two together, we get the sum to k plus 1, right? And this, remember, our induction hypothesis was assuming that this is precisely equal to that for n equals k. So then we can just apply that here. So I'll just do it down here. And what we have is, this is, we'll convert this into this form, right? So this is that for n equals k, and then plus the rest of this, so I'll just attach it onto here. And so now we can compare, we have this and this, which both have coefficients of A, and then this and this, which both have coefficients of B. So we can group them together, and we can pull out the A, so I'll just do it this way. So we have A times this sum plus F sub k plus 1. Well, if we group them together, this is the sum from 1 to k plus 1, right? So I equals 1 to k plus 1, and then, of course, of F sub I. And then we can do the same for B, right? We can pull this out, this coefficient out, and then take the sum again to k plus 1, because here we have G sub I from 1 to k, and then plus G sub k plus 1, and all this is, G sub I, right? And what we have now is A times the sum to k plus 1 of F sub I, plus G times the sum to k plus 1 of G sub I, and this, we said, is equal to this, and we just did it because this is true, and we showed that it's in this form with n equals k plus 1, So we showed the base case, the induction step, and that means that we actually proved our statement for all natural numbers n. So yeah, that's the little induction proof, so I hope you enjoyed. Thank you so much for watching, and I'll see you in the next video. Bye guys!